Okay, so been introducing speakers right along, and we'll be continuing to do that, but in this case, I am the speaker, so I'm introducing myself again. So, again, I'm Dick Wilkins from Phoenix Technologies. What I do for Phoenix is my official title is Principal Technical Liaison, whatever the heck that means. Anyway, I'm responsible for interfacing with standards groups like UEFI, TCG, DMTF, PCI SIG, Bluetooth, T10, T13, et cetera, et cetera, et cetera, et cetera. It's my job to keep track of what all these groups are doing and report that back to Phoenix and try and encourage them to do what Phoenix thinks is the right thing to do. For UEFI specifically, I sit on the board of directors representing Phoenix, and I also chair the UEFI security response team that handles security incidents with our firmware. So if anybody out there in the world reports security incidents with our firmware, our team responds to that and gets information out to everybody so we can get that fixed as quickly as possible and deal with it. And also negotiates with the reporters for reasonable and equitable disclosure of that information to make sure that we don't give zero-day attacks to people out there. So anyway, so that's what I do. In particular today, I'm doing a presentation. It's called TPM 2.0. The specs are here, now what? I actually did a presentation on this at what we called then a Summerfest event in 2013 at Microsoft. And I said basically TPM 2.0 is here, we need to start implementing. Now it's 2.5 years later and we still are not there yet. So I want to talk about that. Give a little bit of background on the TPM. What's happened, what's ready to go, what still needs work, and a call to action, of course. So, as I said, I did a presentation on the TPM 2.0 in 2013. Described the minimal necessary interface changes required to talk to the hardware. A TPM chip, whether it's a chip or a firmware simulation, emulation of that chip. I talked about the minimal stuff that is necessary to talk to it. But TCG really hadn't worked out the changes necessary to support the chip. And for the past 2.5 years, they've been meeting continuously, figuring out what it really means and coming out with new specifications describing how to interface to that chip and what's involved. So they're finally publishing their stuff. First of all, there are many of you in the room that probably heard of TPM, but you don't routinely use it in your business. And so I want to quickly, just as a reminder and a refresher for those who are not familiar, TPM is a trusted platform module. It was specified by the Trusted Computing Group. It's their primary product. And it's actually produced by a number of silicon vendors that produce versions of that TPM chip with some variation in capabilities. It provides protected storage for keys and certificates, a platform configuration registers, what I'll talk about, and cryptographic engine. And first, PCRs. What the heck are these things? Platform configuration registers. They're hardware registers that can only be reset and the term extended in that they take a hash of the current value of the PCR and some blob of data that's supplied to it at the same time, hash that together and store it in the PCR. And that can be repeated as many times as necessary to hash blobs of data and record them in the PCR. And when you stop, it holds that state, the value of the hash in that PCR until it's reset again. The idea here is this is a very similar process to what we do with Secure Boot. In that Secure Boot, we essentially hash our executable images and decide whether that ending hash code matches a certificate that was supplied when they were originally created, and decide whether we will execute them or not. In this particular case, what we're doing is we can take code images, variables, basically any binary data, and store them in these PCR registers and come up with values at the end. And they become available for checking in the future. We also create log entries of what we're doing along the way. So if the values we end up with at the end don't match pre-stored values, we can kind of go back and figure out what happened. How did we get here? What went wrong? What this creates is the ability to do what's called measured boot. Secure boot essentially just says that we will not execute code images that are not properly signed or don't match their signature. So if they've been hacked in any way, we won't execute them. That may well prevent the system from booting. It may not, depending on exactly what they are. But it will not allow damaged code to be executed. In the measured boot situation, we'll go ahead and execute it. And we'll boot the machine up as best we can. But at the end of the process, we will have a measurement that indicates that something went wrong along the way. Some setting changed, a code image was damaged or hacked or something, whatever. And at the end of that process, we can authenticate that information with a copy of the PCR registers and the log using the NIST guideline 800-155 from the U.S. Department of Commerce, National Institute of Standards and Technology, their guidelines for how this should be done. Essentially, we can send a copy of the PCRs and the logs to an authentication server who can compare those against a pre-recorded version of those PCR values and say, did this system boot securely? Did all the settings stay the same? Did all the code the same as it was before? If it was, it can use potentially a network access control device and allow the system to join the corporate enterprise government network or whatever. If, on the other hand, they don't match, that system using the same network access device potentially could be sent to a subnet on a remediation server who, and that system, as the system potentially is insecure. Something's wrong with it, needs to be remediated, needs to be repaired. And that remediation server can then go through the log and figure out what probably happened, what went wrong, and how to fix it. And it can reflash ROMs if it needs to. It can change settings. The nice thing about this is if your corporation, your enterprise, or your government agency decides that you want a specific boot order, and you don't want to boot off of USB sticks or something like that. If a user goes in and changes the settings in the system to allow that to happen, that will change PCR values and will cause that system to be handed off to a remediation server, and the settings changed back and the system rebooted before it's allowed to join the corporate network. So it allows not only checking of damaged code, but also any sorts of settings, hardware, anything you want to check can potentially be stored in PCRs. So this is not secure boot, as in the UEFI spec. It's something else enabled by the TCG specs. There's also sealed storage on board. This is used by many pieces of software and OSs out there to store things like keys. BootLocker, for example, if the TPM is present, will attempt to store its cryptographic key for unlocking drives in the TPM chip, where it's pretty safe. Just an aside, somebody claimed that they broke a TPM chip and were able to access it and watch its cryptography going on and find out the keys and that kind of thing. And no one has said that it's unbreakable. They make it hard, but it is potentially breakable. And what they did was they actually disassembled the machine, took the chip off the board, placed it on a special board, ground the surface down so they could get access to the silicon, and then went in with an electron microscope, $5 million US, in order to watch what was going on in the chip. And then it took them a month or two to figure out exactly what was going on and decrypt it and find the keys. So yes, at that level, you can break a TPM chip. But it's going to cost you $5 million in electron microscope and a lot of time and effort to be able to do it. So it's, for what the goal is, it's reasonably safe. So essentially, the process here is you supply the TPM chip with a blob of data that you want to secure, cryptographic key or something like that, and the current settings of the PCRs that you care about. You don't have to specify all of them, potentially specify none of them, but the PCRs you care about to say the system has securely booted up. And then if you want to unseal that process of the PCR's values and the blob of data is sealing that in secure storage. But if you want to get that key back at any time in the future, you have to supply a value. The values in the PCRs must match the current values that are set in the hardware. And then you can retrieve that data out. So you can only unseal and get the cryptographic key or whatever else you stored in the small amount of memory there if the system has securely booted up. So it's a reasonably secure way to store things. That's why Microsoft requires it, and because they really believe that we should be doing this. I just mention this because it becomes interesting to a lot of folks. What was the difference between the TPM 1.2 and 2.0? Basically, TPM 1.2 supported these algorithms and only these algorithms. SHA-1, which we all know is dangerously insecure, and several of these. The nice thing is TPM 2.0 can support any hash algorithm with a fixed digest size, which is most of them. Any asymmetric algorithm that has public and private keys, and any symmetric algorithm as well. You just have a single key. So the hardware will support any of them, the cryptographic engine. So you can use any one you want. This is really good for if you sell into a geography that has government restrictions on the type of cryptography that can be used, because the TPM chip can be used in that environment. It can use whichever algorithm you choose to. So it's not restricted to some limited set that may be illegal in certain geographies. So it's really helpful in that environment. Okay, that's the refresher on what a TPM chip is. It's important to the marketplace. Microsoft said yesterday they require for their platforms running Windows 10 that it needs to be running at TPM 2.0, and they're going to make that a hard restriction in the very near future. I can expect that. I'm not going to speak for Microsoft, but I know that that's the indication. The PC Client Working Group has finally released, this is the TCG organization, has finally released specs describing how firmware should implement TPM 2.0 functionality. Most of you out there are not paying attention to this. I looked at the roster of membership, and I looked at the active participation in the PC Client Working Group that does all the work on these specifications. Microsoft, me from Phoenix, and a handful of OEMs, Dell in particular, Lenovo, are actively involved with the TCG PC Client Group. None of the rest of you were active, and most of you are not even members of that organization. This is really important to a lot of you, that you really need to be paying attention to this stuff. Code changes are coming as a result of these new specs. And here's the new specifications that matter. The PC Client Platform Physical Presence Interface specification was published last summer. This one's been out for a little while now. The PC Client Platform Firmware Profile specification. This is a new name, a completely new spec, It's still in draft. It's under public review. You can go to their public website and download it and take a look at it. It's available now for public review. There's going to be some errata, and there's a couple of niggly little items that are still being worked out before it will be published. But I would expect it to be published in the next 2 or 3 weeks, unless there's enough change that requires them to go through another 60-day formal public review. So there's some debate about that. So it might be 2 or 3 months, it might be 2 or 3 weeks before it becomes available. Note, this has been completely rewritten from the ground up. The old spec talked primarily about conventional legacy BIOS, and then had a couple of chapters that said, and by the way, here's this UEFI thing, and here's how it's different. This spec, they've completely done away with legacy BIOS. It's not mentioned. The new spec is entirely UEFI. It basically said if you're using TPMs and the TCG specifications, UEFI is it. There is no other system to use it. So UEFI is the world. And finally, they provide their own EFI protocol. You're all familiar with protocols and calling protocols. They provide their own in their own specification, and they call it the EFI protocol. And this provides access to the TPM chip from OS, that kind of thing. So that is publishing today. It was officially completed last week, and it should be appearing on the website sometime today. So the final version is available almost immediately. Okay. Back in 2013, I talked about just the low-level interfaces. I didn't know anything about what these specs were going to have in them. Now the specifications are here, and they're almost all completely published. Code changes are going to be required. Every UEFI platform out there is going to have to change to support these new specifications. Every single one. So, and they're significant code changes. Not massive amounts, but they are significant. And they're not out there in the open source space at all. I shouldn't say at all. There's some of them that are there, and there's some of them that are there that are wrong, and there are some that are just not addressed at all. So, what's there now? I'm not going to read these slides to you. This is iChart. These are things you can go on the website and look at later. But I'll just give you sort of the headlines of these. Anyway, there's the original protocol that was in for 1.2 has been completely subsumed by the EFI TCG2 protocol. And it provides a bunch of interface changes and additional interfaces that are required by the new chip. The physical presence interface and the big difference between TPM 1.2 is TPM 1.2 had a whole bunch of different states: enable, disable, activated, deactivated, various states here, and forest clear. There were a whole bunch of states that you could have, and it was bizarre, and you had to kind of stand on your left foot and jump up and down 3 times to get the chip to go into the right state. It was very confusing and very hard to implement. They got the message. They heard the story and said they simplified it to a much simpler set of states, much easier to implement. It's basically kind of on and off. And made it a whole lot easier to implement. But it means the code has to be completely changed to support these new states. The event logs, which I mentioned, are critically important to figure out what went wrong. If the PCR values change from one boot to the next, you need to understand where things changed. And the only way to do that is by parsing the log and figuring out where things changed. So where the logs are and how they're formatted is critically important. That's a big chunk of what the PCI, the TCG spec for TPM 2.0 is about. I think the biggest change in the way the logs are accessed used to be in the TPM 1.2 time frame. The event log could be located in the ACPI tables, and you could just read it out of ACPI space as if it was another table. That has been removed. You need to use the UEFI protocol and do the git event log operation in order to access the event log. So an OS could, in the previous days, look it up in the ACPI tables and find the event log. You can't do that anymore. So the format of the ACPI tables has changed. The rest of this is detail that you can look at offline. I'm not going to read all that to you and go over there. So that was stuff that was in EDK2, but has not been adopted by some of you. Some of you have older versions, have not adopted the recent drops and all that, may not have adopted all that stuff, even though it's actually out there in the open source code base today. Now here's the stuff that's not in Tiana Core or EDK2. It's not done yet. No one's done that work. And I should say, the little line here says, thanks to David Luke from Phoenix. He did a lot of work to find all this stuff for me. I didn't spend a huge amount of time reading code to make sure what was there and what wasn't, so I want to thank him for that effort. So there's a bunch of changes specified in the TCC specifications that are not in this code base. This is not an exhaustive list. I'm not claiming that we went through and found absolutely every change, but we hit the high points. Most of the important ones are here. There's a lot of work that needs to happen by everyone out there in order to get this. At the very least, you're going to have to adopt a newer version of the Tiana Core EDK2 codebase to pick these up once they're in there. But as Tony was saying, we need contributors to go through and develop the code that I'm going to be talking about to implement these changes. And they're a significant amount of work. A lot of it has to do with error cases. If the startup command fails during initialization, you must either reset the device and try again, or you must totally disable the TPM. So obviously, you might, if it fails its self-test and won't initialize, you might want to try again once. But if it keeps failing it, you don't want to keep trying again. You'd be stuck in a loop and never boot. So you might want to just disable the device. So David actually made a proposal here, reading the spec. Nowhere in the spec does it tell you how to do that exactly. But his recommendation, that's up for discussion, is to essentially, if we want to make the TPM invisible, turn it off, you have to use the TPM2 hierarchy control and disable the hierarchy, essentially, which essentially turns off the chip. It makes it unusable and unavailable, and essentially turns it off. That's his proposal. Some developers need to get together and have a discussion and say, is this really the right way? And maybe work with some of the chip vendors to confirm this is the right way to do it, but we believe that it is. The PCRs, they have to be managed in a very specific way, and the PCRs 0 through 7 are very specifically used. One of the things the TPM 2.0 chip allows you to have many more PCRs than you used to have. So, but the first eight, are specifically designated for specific uses. And in error circumstances, they have to be set in very specific ways and handled in very specific ways. And the code doesn't do this. I'm not going to go through and give you all the gory details here. But these will be available on the website for reading later. Then specific PCRs have to be dealt with in specific ways. Again, this is PCR 0, and in event of certain errors, you have to do certain operations. These are not in the code base currently. So somebody needs to code this to make it work. If the firmware loads a microcode update, it must be measured using a specific event code in the event log, and it needs to be put in PCR 1. as this bold text here basically says, you don't need to read all the gory details here, what it says is basically, this has been done, but it's been done wrong, and right, and wrong, and right, and right now the code base has it wrong. So it's just flat out recording this into the wrong PCR. We need to fix this. Other PCRs, if you want to, PCR4 is a PCR where you record boot events so that you can keep track if a boot starts and then fails, and then starts again and fails, and starts again and fails, and tries to boot from several devices to keep track of that. If you don't want that information to be recorded so that it appears as a change, if it boots differently each time, that's possible to do that, but you need to make sure that you specify in the event log and measure the fact that you're not going to, say, keep track of the boots in the event log. And again, this is not being done currently. PCR6 has now been specifically set aside for OEM use. So you OEM representatives out there, if you have things that you specifically want to measure and control and keep track of during boot on your platforms and record, PCR6 is the place to do that. It's been used various ways at various times. They finally came down and said, okay, this is it. This is for OEM use. Other OSVs out there have tried to use PCR6 for their own purposes. They need to stop. So if any of you are not an OEM, not a platform manufacturer, and you're using PCR6, you need to stop doing that. There are other PCRs available for that kind of thing. PCR6 is reserved for the platform manufacturers now. PCR7 is one of the areas that's still under discussion. It's under the new 2.5, new at the time 2.5 UEFI spec. We added, and we talked about this in the first presentation yesterday, audit mode and deployed mode and the DVR and DVT databases and that kind of thing. These get measured into PCR7. But what happens when they change during the boot process? There's a debate going on right now in the spec working group of whether if you change one of these, then you need to just reset and go back to the beginning and start boot all over again. Or whether you can just measure the fact that you changed them into the register and continue on. That's the current debate. So right now, I think the wording in the spec is you can do either one, but you have to do one or the other. Either reset it or measure the fact that you changed them. But re-measure those variables. But that may change. And PCR16, another one, has now been set aside for debugging purposes. Now we actually have a reserved PCR that's set aside. If you're trying to debug this stuff, you can measure anything you want there, extend that, and use it for debugging purposes. So that's permanently set aside. Again, support for that is not in any of the code currently. Another case here, physical presence and platform hierarchy. Basically, it's saying that if something goes wrong, the platform hierarchy needs to be protected. And so there's a particular operation that needs to happen. The code's not currently doing that. So, in summary, all the IBDs, OEMs, OSVs, etc. need to make aware of these changes. It matters to IHVs probably if you do option runs. If you don't do option runs, you probably don't care. But if you have option runs, you probably do care about this stuff. We need to make these code changes. We need help from the community to get involved and design and write these code changes. So this classic open source development effort, we all need to have this done. This is not a place where we're going to do proprietary extensions or value add features. This is common code that everybody needs to use and everybody needs to use correctly and in the same way. It's a perfect situation for an open source participation. So we need engineers to develop these code changes. And as I said, the TPM 2.0 is mandatory So all these changes are, now that this is published, all these changes are mandatory as well, as quickly as we can get them in there. So, questions on any of that? Donation.
I have a question. What is the position of the TCG on making TPM 2.0 parts available to development? Because I know the last time I checked, it was very hard to find TPM development platforms, right? To code against, to test against, to debug against. For instance, the last time I checked, I could only find TPM 1.2, right? But you can't find a TPM 2.0 development platform. So how does TPM use this?
Okay, Tony's asking about TPM 2.0 development platforms. Are chips available? When I first did the original presentation back in 2013, they were just sampling a handful of chips. There were almost no chips available. Nowadays, TPM 2.0 is in volume shipment from most of the silicon vendors, the Infineon and et cetera. So the chips should be available. Now, a specific development platform?
Yeah, the chips aren't sold on a one-by-one basis, right? And they're not sold in the development mode, they're sold in the production mode. And then the third problem is that the specifications for those chips are only given under NDA with the specific TPM company. So, I can tell you from the open source perspective on the EDK, we have had a project where we enabled TPM 1.2 on Galileo, but the only way we did that was because an Intel engineer poked and prodded at each of the registers and he didn't figure out what each one of them does, and then reverse engineer the code, right? Because that particular vendor wouldn't give us the specification for what the pins do on the chip and how to actually exercise and use them. So, if the TCG wants us to implement an open source, we're going to have someone step up and say, here's the platform you can do.
That's a good point. So, for repeating for the people in the back of the room that obviously can't hear Tony, it's basically saying that if we're going to do open source development, we need access to a development environment with chips and documentation from the vendors involved so that we can actually develop this stuff. And it's fine for an OEM and maybe their IBV who's buying thousands or millions of these chips from a particular vendor. They can go to that vendor and negotiate a deal to get access to the stuff. But if you're in the open source community and you don't have the ability to just buy one or two of these chips in a development environment and get them to disclose the details of the implementation, I will carry that back to the TCG group. I know as far as getting the details on how to access the chips, under the PC client group, there's a driver development group, there's a working group, and that's where we discuss the actual manipulation of the chip and running it, and all the vendors are there, and any TCG member company is welcome to join that group and participate and ask questions and send emails to the right people and all that. So there's a way to get contact if you are a TCG member, but that would be sort of a side channel.
Right.
So I will carry that back.
Thanks, Dave.
Other questions? Anything at all? Okay, our next speaker